Somewhere, 400,000 miles past the orbit of the moon, a gold-coated mirror the size of a tennis court is staring into a place that should not exist. Not a black hole, not an alien signal. Something quieter and somehow more disturbing to the people whose entire careers were built on knowing how the universe works. A galaxy? Just a galaxy. Except this one was fully formed, fully massive, packed with stars, sitting in a part of the sky that represents a time when the universe was only 280 million years old. For context, that is roughly 2% of the universe's current age. It is the cosmic equivalent of finding a fully grown adult standing in a delivery room. Oh, and it is not the only one. Astronomers now have a name for what they keep finding out there, and it is not a flattering one. They call them impossible galaxies. Because according to the physics that has guided cosmology for nearly a century, these things simply should not be there. Not yet, not this early, not this big. And every single month, the James Webb Space Telescope finds another one. Quietly, patiently, dismantling assumptions that were considered settled science before it ever left the ground. This is not a story about a telescope taking pretty pictures. This is a story about a machine that was built to confirm what we already believed about the birth of the universe, and instead has spent the last several years handing scientists one uncomfortable surprise after another. Some of the world's most respected astrophysicists are now openly saying that our models of galaxy formation need to be rewritten, not adjusted, rewritten. Let's rewind for a second, because you need to understand what Webb was actually supposed to do. When it launched in December 2021, riding an Ariane 5 rocket built through a partnership between NASA, the European Space Agency, and the Canadian Space Agency, its main job was to look further back in time than any instrument humanity had ever built. Light takes time to travel, so the further away something is, the older the light is when it finally reaches us. Webb's mirror, 6.5 meters across and built from 18 hexagonal gold-coated segments, was designed to catch the faint infrared glow of the very first galaxies, the ones that formed in the chaotic aftermath of the Big Bang. Scientists expected small, faint, messy blobs of young stars, primitive building blocks. That is not what they found. This isn't even the first hint of trouble. Years before Webb launched, the Hubble Space Telescope caught an early warning sign on a surprisingly bright galaxy called GN-Z11, existing just 400 million years after the Big Bang. At the time, it was the most distant galaxy ever confirmed, and it was already brighter than it had any right to be. Astronomers noted the strangeness and largely assumed it was an outlier. Webb was supposed to settle the question and move on to the calm, orderly galaxies scientists expected to dominate the early universe. Instead, Webb confirmed GN-Z11's extreme distance and then kept finding more galaxies just like it, brighter, earlier, bigger. What looked like a one-off exception turned out to be the first crack in the wall. As one member of the MOEM Z14 research team, graduate student Yijia Lee of Penn State, put it, it's an incredibly exciting time, because Webb is revealing the early universe like never before, showing scientists just how much there still is left to figure out. That's the polite, careful academic way of saying, we thought we understood this, and we were wrong. Here's why that jump from Hubble to Webb matters so much on a technical level, because it's not just a bigger mirror doing the same job better. Earlier telescopes like Hubble were built primarily to see visible and ultraviolet light, but by the time light from the very first galaxies reaches us, the expansion of the universe has stretched it dramatically, shifting it out of the visible spectrum entirely and into the infrared. Hubble could see the young, hot blue stars flaring on a galaxy's surface, but it missed the older, cooler, more massive stellar populations hiding underneath, the ones that actually carry most of a galaxy's true mass. Webb's infrared instruments were purpose-built to see exactly that hidden material. And when scientists finally pointed Webb's infrared eyes at galaxies Hubble had already mapped, entire structures appeared that were completely invisible before. That's exactly what happened with the Big Wheel. Hubble saw scattered clumps. Webb revealed an entire massive rotating disk hiding in plain sight underneath. One of the clearest examples is a galaxy called MOEM Z14. Using Webb's near-infrared spectrograph, astronomers led by researcher Rohan Naidu at MIT's Kavli Institute confirmed this galaxy sits at a redshift of 1444, placing it just 280 million years after the Big Bang. And it is not some faint smudge. It is bright. Genuinely, surprisingly bright. Bright enough that it forced the research team to admit their own predictions were wrong. According to the team, galaxies like this one are showing up roughly 100 times more often than theoretical models predicted before Webb ever launched. 100 times. That is not a rounding error. That is a sign that something in the underlying theory is broken. Here's where it gets stranger. It's not just that these early galaxies are bright. It's that they're organized. Take the galaxy nicknamed the Big Wheel. Webb discovered it, sitting in a field originally chosen because of a bright quasar nearby, and what it found there stopped astronomers in their tracks. A massive spiral disk galaxy, 5 times more massive than our entire Milky Way, complete with visible spiral arms, existing just 2 billion years after the Big Bang. Spiral arms are fragile. They get disrupted by collisions, by gravitational chaos, by the sheer violence of a young, crowded universe. And yet, here was one, fully intact, fully massive. At a point in cosmic history when everything was supposed to still be a disorganized mess, Hubble, looking at the same patch of sky and ultraviolet light, only ever saw scattered clumps on the outskirts. It took Webb's infrared vision to reveal that underneath those clumps was an entire, coherent, rotating disk that Hubble had been completely blind to. The scientists studying it put it bluntly, this discovery is a demanding test of how galaxies grow, and right now, the models are failing the test. In January 2026, a team from Texas A&M University, led by postdoctoral researcher Wei Hu and Professor Casey Popovich, identified an active Dick-Prowse tightly packed collision, at least 5 galaxies merging together, only about 800 million years after the birth of the universe. They nicknamed it JWST's Quintet. The collision was actively redistributing heavy elements like oxygen, flinging them out beyond the galaxies themselves. Astronomers expected this kind of complex merger and chemical enrichment to become common only after more than 1 billion years had passed. This was happening hundreds of millions of years ahead of schedule. Professor Popovich said it plainly. This tells us that our theories of how galaxies assemble and how quickly they do it need to be updated to match reality. It doesn't stop there. A separate team, led by researchers at Leiden University and the University of Oxford, turned Webb toward a source cataloged as TGS-SJ 1530 plus Seno 49, expecting to find one galaxy housing an actively feeding supermassive black hole. What they found instead was an entire construction site. At least 6 galaxies, packed together in a region only a few tens of thousands of light years across, all merging into a single colossal system. 4 of those 6 galaxies were already surprisingly massive on their own, together holding hundreds of billions of solar masses worth of stars, crammed into a space that, on cosmic scales, is almost claustrophobically small. This is happening in a universe only about 1.5 billion years old at the time. Researcher Ayush Saxena of Oxford said it best. They went looking for a single black hole and instead found an entire complex of galaxies feeding it. There's also a discovery that quietly undermines a relationship astronomers thought they understood. In nearby galaxies, there's a well-established pattern. The mass of a galaxy's central black hole tracks closely with the properties of the galaxy around it. It's one of the more reliable rules in modern astrophysics, built on decades of careful measurement. But researchers at Carnegie Science used Webb to measure, for the first time, the mass of a now dormant black hole from the early universe, inside a galaxy called MRG M0138. What they found suggests that in the densest environments of the early cosmos, black holes were growing explosively fast, likely powering a quasar phase violent enough to blast away the very gas that fuels star formation, effectively shutting the galaxy down early. In other words, some of these ancient galaxies may have burned out young, their growth cut short by the very black holes sitting at their hearts. It raises an uncomfortable question nobody has fully answered. If black holes were already this dominant this early, was the relationship between galaxies and their black holes actually built the other way around from what we assumed? Then there's a galaxy that breaks a different rule entirely. Not a rule about size or speed, but a rule about motion itself. In a study published in Nature Astronomy, researcher Ben Forrest and his team at UC Davis studied a massive galaxy that formed less than 2 billion years after the Big Bang. Under normal circumstances, young galaxies are expected to be spinning, gas flowing inward, gravity pulling, angular momentum building, the same way water spirals down a drain. This galaxy, catalogued as XMM Vid 12075, showed no evidence of rotation at all. None. That is a trait typically reserved for much older, much more evolved galaxies, ones that have had billions of years to settle into that kind of quiet, static state. Forrest called it surprising and very interesting, which in scientific language roughly translates to, we don't fully understand what we're looking at. This galaxy had already stopped forming new stars, already packed in several times the stellar mass of our entire Milky Way, and already skipped the spinning phase every model says it should have gone through. It's as if this galaxy fast-forwarded through its own life story. Even the shape of galaxies in the young universe is turning out to be stranger than expected. Researchers at the University of Waterloo, digging through Webb's observations of the cosmos field, identified the most distant jellyfish galaxy ever recorded, a galaxy trailing long, tentacle-like streams of gas and newborn stars as it plows through a dense cluster, exactly the way real jellyfish trail their tendrils through water. This particular galaxy is seen as it appeared 8.5 billion years ago, and its existence tells astronomers that the early universe may have been a far more violent, turbulent place than the calm, orderly picture painted by earlier models. Galaxies weren't drifting peacefully through empty space. They were being ripped apart, stretched, and reshaped by forces far stronger than anyone anticipated. Now, physics being wrong about galaxy formation is one thing. It's a big thing, don't get me wrong, but it's still physics arguing with physics. What happened next edges toward a question every one of us has asked while looking up at the night sky. Are we alone? In the atmosphere of K2-18b, a planet orbiting within the habitable zone of a red dwarf star roughly 120 light-years away, Webb detected dimethyl sulfide, a molecule produced almost exclusively by living organisms on Earth, mostly marine phytoplankton. Its presence in an alien atmosphere would be, without exaggeration, one of the most significant scientific findings in human history. Here's the responsible part of the story, though, the part a lot of headlines conveniently leave out. The signal currently sits at a 3 sigma confidence level, meaningful, but not yet the 5 sigma threshold that astronomers and physicists require before they'll stand behind a formal claim of discovery. NASA itself has been careful and precise about this, stating plainly that they are not claiming to have detected life on K2-18b. What they are saying is that they've found a chemical signal significant enough to demand urgent, serious follow-up investigation. That's not a letdown. That's how real science is supposed to work. No premature victory laps, no manufactured certainty, just a genuinely tantalizing signal the entire astronomical community is now racing to confirm or rule out.